Here again, we're going to relate our position versus time graph to a velocity versus time graph. So look at what this graph is doing and try and think about what the velocity, the corresponding velocity should be. Remember, you're really just looking at what the slope here is doing and how the slope changes. So take a second, press pause, take some time to choose your answer, and then press play when you're ready to come back. Well, what I see is a negative slope, and that slope is roughly constant for a little bit. So I want a value that's negative and constant. This is really the only one that has a negative constant value. This has a negative value, but it's getting more and more and more negative. This slope in the beginning is roughly constant. I have roughly a straight line here. So I want something that's basically constant but negative. Then the slope becomes less and less negative and approaches a zero slope. So I want something that becomes less and less negative and approaches a zero value. So C is the correct answer in this case. Now we have a velocity graph, and I want to just figure out when does the object turn around. So take some time to think about that. Well, turning around means that the velocity goes from either a positive velocity to a negative velocity or a negative velocity to a positive, and that happens right here at t equals 8 seconds. So the answer is B. Right at that moment, the velocity is 0, and that's when it's changing directions or turning around. We have the same graph here, and we want to just describe the velocity. Just think about, where is it speeding up, where is it slowing down, where does it turn around, does the object ever stop? Think about all those types of things and just take a second to try to describe it, and then press play when you're ready to go over it. So what I would say is, in the beginning we have an object. It's moving in the positive direction because the velocity is positive, and it's going faster and faster and faster and faster and faster up until t equals 4 seconds. So this whole time it's speeding up. It's going faster and faster and faster. Remember, this is a graph of velocity. Now at t equals 4 seconds, it doesn't turn around, but this is at the point where it starts to slow down. It's still going in the positive direction, but it's going slower and slower and slower and slower and slower. And then right here at t equals 8 seconds, this is the moment that it turns around. For this one moment, the velocity is 0. It's not moving. The object is at rest right at this moment. And now after that, it starts moving in the negative direction. So it's moving to the left, and it's going faster and faster and faster and faster. And at t equals 10 seconds, it doesn't stop because the velocity is not 0, but it starts to move at a constant velocity. Still in the negative direction, but it just has a constant velocity, so it's not changing its speed after this. Let's see how we can look at a velocity versus time graph, and from that get information about our displacement. So here I've just taken our equation that we've been using. Here it's rearranged to our normal uniform motion equation, and v is this value here. Delta t is like this width. If you do v times delta t, that's just the area of this rectangle. So we can say the total displacement, delta x, is the area under the curve of a velocity versus time graph. Well, that works very nicely when our velocity is nice and constant. But what if I had a velocity like this? How do I find the area underneath here? It's still true the total displacement is the area, but how am I going to calculate this area? This is an approximation, but I have this extra little bit here. What if I chop this into tiny little chunks, tiny little rectangles, and measured the area of each of these rectangles? I'd be much closer to my answer. If I made these rectangles teeny, 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 tiny, and added all of them up, I get a really good value for that total area. So what I'm describing, of course, is an integral. And this part here, don't let it scare you. If it scares you, just hold your hand up in front of the screen and block that part. Don't write this part down if it scares you. But all I'm trying to do here is just really tell you what an integral is. We're taking tiny little rectangles. We're trying to figure out this whole area. So I'm taking tiny little rectangles and finding the area of one tiny little rectangle. And I'm making those rectangles as narrow as possible. And then I'm just adding them all up. And that's the same thing as taking an integral. So another way to think about the total displacement is that it's the integral of the velocity. Now this is total displacement. It's not the final position. It's just the displacement. If you want the final position, you'll have to figure out, you have to be told what the initial position is. So here we have a velocity versus time graph. and I want to know what is the total displacement after 10 seconds. Okay, so what I need to do is take the area all the way up to 10 seconds. And let's be careful because this area here is a positive area and this area here is a negative area. So this area is just the area of the triangle, which has a formula of 1/2 base times height. So it's going to be 1/2 times 8 times 4, which would be 16. So the displacement from 0 to 8 seconds is positive 16 meters. And then I need just the area of this triangle, which would be 1/2 times this base, 2, times this height, 2, but it's negative. So that would be 1/2 times 2, or just 2, but it's negative. So here I had 16 plus negative 2. That gives me 14 meters. One way to think about it, here we're moving the positive direction. We move forward 16 meters, but then we turn around and we move back 2 meters in the negative direction. So our overall displacement is 14 meters. Now they've given us the initial position of 3 meters, and I want to know where is the object located at t equals 10 seconds. So press pause and try to work through that. Well, we just found that the displacement was 14 meters total. That's delta x equals x final minus x initial. X initial was 3 meters. So that means that after a displacement of 14 meters, we end up at a position of 17 meters. And finally, one more, try to tell me the total distance traveled. Again, this is just to help us distinguish between the concept of total distance traveled and displacement. So press pause and think about it. Well, we calculated before, here we have a displacement of 16 meters. Here we have a displacement of -2, but when we're talking about total distance traveled, I don't care about the negative. So it's like here you walk 16 meters, here you walk 2 back towards the left. In total, you've walked 18 meters.